The Physics of Interstellar Travel, Chapter 8, Nuclear Rockets. In a chemical rocket, the kinetic energy of the propellant is obtained from chemical bonds by burning the fuel. This releases no more than about 10 megajoules per kilogram, which limits the effective exhaust velocity to about 4.5 kilometers per second. Nuclear rockets, in contrast, can release the much larger binding energy between nucleons of order 10 to the 8 megajoules per kilogram. If all of this could be converted into kinetic energy of the exhaust, it would produce an effective exhaust velocity of about 14,000 kilometers per second, or around 5% the speed of light. In the previous chapter, we looked at the theoretical aspects of relativistic rockets, rockets which convert a meaningful fraction of their mass into energy. In this chapter, we look at the nuclear and particle process that can achieve this and how they could be used in rockets. Nuclear fission is the process in which a large nucleus is split into two or more smaller ones, thereby releasing some of the nuclear binding energy. A familiar reaction is the fission of uranium-235 as used in nuclear power stations. But how can we capture this energy to propel a rocket? Perhaps the simplest thing we can do is to use the energy to heat an inert propellant, such as hydrogen. We can achieve this by passing the propellant gas over the hot fuel rods in the reactor. Note that the gas remains inert. It doesn't undergo any reactions. This is then just a thermal rocket of the type we discussed in Chapter 5. There we found that the effective exhaust velocity depends on the temperature of the gas in the chamber and on the molecular mass of the exhaust. It's difficult to achieve a very high temperature without melting the fuel or the combustion chamber, so the temperature achieved in a thermal fission engine is actually similar to that for a chemical engine, say around 2500 Kelvin. But by using a lighter exhaust, hydrogen with an atomic mass of 2 instead of water with an atomic mass of 18, we get a larger exhaust velocity. But it's still only 8.5 kilometers per second, which is only twice that of a hydrogen-oxygen thermal rocket. It's the thermal limit of the materials that prevent us from extracting a higher temperature from the nuclear reactions. To overcome this limitation, we should use the product nuclei of the fission reaction directly as the propellant. This is the idea behind the fission fragment rocket. To achieve this, the nuclear fuel is arranged not into rods, but into small dust grain-sized pellets. The fission products have extremely high temperatures, so they cannot be collimated into a propellant beam using the usual physical nozzle. However, as the fission products are charged nuclei, they can be collimated using a magnetic nozzle. This has the same function as a convergent-divergent nozzle used in thermal engines, namely to convert random thermal motions into linear motion, but is achieved with a magnetic field. When powered by uranium-235, such engines could achieve effective exhaust velocities of a few percent of the speed of light. But as it's hard to react a lot of material rapidly, the mass flow rates are low, yielding thrusts of only a few tens of newtons. Journey times to Alpha Centauri with such engines will probably be around 1,000 years. Nuclear fusion is the process by which light atoms combine to make heavier atoms. Because of the way the binding energy per nucleus varies across the periodic table, fusion of light nuclei also releases nuclear binding energy. An example reaction is the fusion of deuterium and tritium. These are heavier forms of hydrogen with 1 and 2 neutrons respectively. This reaction produces helium and neutrons and is being explored as a source of heat to use in future commercial fusion reactors here on the Earth. For a rocket, we instead want to use the products of the reaction directly. But because these products have high energies, we again have to collimate them using a magnetic nozzle. However, in this deuterium-tritium reaction, most of the energy release goes into the neutron, which is neutral and so cannot be directed by a magnetic field. For this reason, the reaction of deuterium with helium-3 is much more attractive, because it puts all of the energy into charged particles, namely helium and protons. The disadvantage of this reaction, though, is that the energy threshold to ignite it is much larger than the D plus T reaction. Furthermore, whereas deuterium is abundant in seawater, helium-3 barely exists on the Earth. It is present on the surface of the Moon in low concentrations and also in the atmosphere of Jupiter. But in either case, its extraction will be complex and expensive. There are other reactions, such as the fusion of two deuterium nuclei, but these all have even higher energy thresholds to ignite. One way to take advantage of fusion as a means of propulsion is the fusion pulse rocket. Here, the deuterium and helium-3 fuel is packed together into small pellets. Fusion is initiated by compressing and heating the pellets with very short pulses of powerful lasers. This is called inertial confinement fusion and has been used to achieve fusion for a very short period in experiments. In the 1970s, a group of scientists and engineers associated with the British Interplanetary Society came up with a design for an interstellar spacecraft based on this idea called Daedalus. This enormous spacecraft has a total mass of nearly 53,000 tons, of which 50,000 tons is fusion fuel pellets. The first stage uses 3-gram pellets, each of which releases 170 gigajoules of energy, and so gives an effective exhaust velocity of 3.3% the speed of light. These pellets are ignited at a rate of 250 per second, which corresponds to an output power of 44 terawatts and a thrust of 7.1 meganewtons. The second stage is similar but smaller, and together these two stages are fired for a total of 4 years. This would give the spacecraft a delta V of about 12% the speed of light, enabling it to travel the 6 light years to Bernard's star, the second closest star to the Sun, in 50 years. This is a mega-scale project, 20 times more massive than the Saturn V rocket that took the Apollo astronauts to the Moon, but that accommodates a substantial payload of 450 tons. A final type of nuclear rocket is the antimatter rocket. This could be based on the annihilation of electrons and positrons, which would create a pure photon rocket. Alternatively, we could annihilate protons and antiprotons, a reaction that initially produces pions, although these quickly decay to muons. Such a reaction in theory delivers a very high effective exhaust velocity of 60% the speed of light. The slight problem, though, is that antimatter does not exist naturally in our part of the universe. It is presently only made in experimental particle accelerators in tiny quantities, about 10 to the minus 11 kilograms of antiprotons per year. Even if we could somehow massively ramp up production, antimatter is extremely hard to store, as it would annihilate if it came into contact with any part of its container. So, if you thought collecting thousands of tons of helium-3 from the atmosphere of Jupiter was hard, that looks easy compared to the challenges of developing an antimatter rocket. That completes our brief look at nuclear rockets. The book chapter goes into more details, both of the basics of nuclear reactions and how they can be used in a rocket, including some methods not mentioned in this video. Fusion rockets are one of the most promising ideas for fast interstellar travel, but there remain many challenges to achieving them.